problem today we are trying to solve is called lowest common ancestor of a binary search tree. So the question given to is given a binary search tree, find the lowest common ancestor. Okay, let's dive into it right away. Okay, okay. Let's say the binary search tree is like this: 6, okay, 4, 7, 2, and 5. All right, and we have okay, let's say only 8. Okay, so the problem given to is they will give us a binary search tree and they will give us two more nodes. Let's say P and Q. Let's say P is here, Q is here. They want us to find the lowest common ancestor of a tree. So in this case, the lowest common ancestor is 6, which is 6 is the only ancestor of 4 and 7, right? But what is actually a low common what is actually an ancestor? So ancestor in this case, in this tree, 6 is the ancestor of all the subtrees and all the elements of the node. So 6 is the ancestor of 4, 2, 5, 7, and 8, all of them, right? Okay. So what if the P and Q are given to is given is 2 and 5, right? So 2 and 5 are have two ancestors now. One is 4 and the another one is 6. So which ancestor should I written? So we have to return the lowest common ancestor. That means this is level 0. This one is level 1 of binary tree. This is level 2 of binary tree, right? So we have to return the level ancestor which is on the lowest level from the ground. This is the ground. The lowest level from here is this one. So this we have to return the immediate ancestor, basically it's a binary search tree. Okay. So let's get right into the algorithm. Okay. So let's say P and Q are given here. P and P is 2, Q is 5. So what we're gonna do is we're gonna see whether P and Q are less than the root. Okay. So we're gonna see if P and Q are less than root. Okay. Then search your ancestor in this tree. Ignore this tree right away. Okay. Search your answer only in this tree. Okay. And if P and Q are on the right side, so suppose P and Q are here. Suppose for example, it's not in the question, but let's say 6.5, just to maintain the constraint, I'm doing this. P is here, Q is here, right? In this case, P and Q both greater than the 6, greater than the root 6. Okay, so only check in this tree. The ancestor is in this tree. We don't have to check this tree right. We can ignore this tree right away. Okay, so so we have two cases now. P and Q less than root, P and Q greater than root. Okay, but what about P and Q are splitting the root in two? So P is 4, Q is 7. What about then? If P and Q are splitting the root in half, we can just return the root right away, right? We don't have to check anything further because we know that the immediate ancestor, whenever the node is getting splitted, 4 and 7 is the one right above them. So this one, right? Okay. So this is the third case. Okay. But there is other cases where suppose P given to you is here, Q is here, or Q is here, or P is here, something like that, right? In this case, what will happen? Same thing, our algorithm will still work. We will say if P is less than Q and P and Q are less than the root, then go left. But in this case, it's not. P and Q greater than the root, then go right. In this case, it's not. Then return the root. Our answer will still be 6. Okay. Same if Q was here, P is here. Again, same. Q and P are not less than 6. Q and P are not greater than 6. Then return 6 right away. Because why does this work? Because 6 is the ancestor of itself. 6 is an ancestor of itself. So all the node is an ancestor of itself. And all the nodes is a descendant of itself. Okay. A descendant of themselves. So that's how algorithm will work. So let's try this now. Let's say if p.val okay, is less than root.val and q.val also less than root.val and return answer, find the answer in the left side of the tree. The left side of the tree. Okay. Do self dot root dot left. P and Q will stay as it is. If p.val is greater than the root.val and q.val is also greater than root.val, we get your answer from the right side of the tree. else. This is the case where P and Q is splitting. So this is the case where P and Q is splitting the root in two. So when P is 4, Q is 7, right? We don't have to check anything further. We can just return the root right node as it is right away. And this will also work when P is here, Q is here, or Q is here, P is here, right? So let's try this one. Okay. So I'm going to submit this. As you can see, it works. So let's see the time complexity of this problem solution. Okay. So in the worst case, if P and Q are less than the root, we are only searching on the left side of the tree, right? We are ignoring the other half. If P and Q are greater than root, we are searching on the right side and we are ignoring the left side of the tree right away, right? So every single time we are breaking the tree in half, right? So that's why the time complexity will be nothing but height of the tree, which is log n, because at the most it can gonna go here, it can go here, right? So right at the most, time complexity will be log n, which is the height of the tree. So O of h, where h is the height of the tree. Okay. Now this h can be log n or h can be n. If it's a balanced tree, it will be log n. We don't know whether it's balanced or not, or if it's not balanced tree, it will be n. This is the time complexity, and the memory will be O of h as well, because if we're gonna have those many call stacks in our stack, right? If we're calling here, and then we're calling here, and then here. So memory is also often, time is also often. Okay. Thank you guys for watching. And the reason I made this video was because I saw two videos on YouTube about this topic from Greg Hogg and from LeetCode. And I thought both of them like made it a little bit complicated than it need to be. By the way, shout out to both of them. I like their videos. Thank you for watching.